Every single day, over 100,000 commercial flights cross the world's skies. Meteorologists track every storm system on the planet in real time. Airlines have access to some of the most powerful weather computers ever built. And yet every single year, thousands of passengers are injured by turbulence that nobody saw coming on perfectly clear days with not a single cloud visible from the window. We can predict a hurricane forming over the Atlantic 5 days before it reaches land. But we cannot reliably predict the air pocket a plane will hit 60 seconds from now. In 2024, a Singapore Airlines flight struck severe turbulence over the Indian Ocean. One passenger died, dozens were injured. The crew had no warning. The aircraft's weather radar showed nothing at all. The reason turbulence cannot be predicted every time is not a failure of technology. It is a basic property of the atmosphere itself, and understanding it will change everything you thought you knew about how aviation manages risk. The obvious answer seems simple enough. More sensors, better satellites, faster computers, more data, better models. But that answer falls apart quickly. The kind of turbulence responsible for the most serious injuries, clear air turbulence, is invisible by definition. Radar cannot detect it. Satellites cannot see it. Even reports from other pilots often come too late to help. 3 problems stand in the way. The first is the physics of how the atmosphere behaves. The second is a gap in what our detection tools can actually find. The third is time. Even when a warning arrives, there is often not enough of it to act. Clear air turbulence incidents are expected to increase by 55% by 2050 because of climate change, while aviation carries 5 billion passengers a year. So the question becomes unavoidable. Is the industry's current strategy of managing turbulence, rather than predicting it, a rational response, or a quiet admission of defeat? Most people assume turbulence comes from storms. It does not, or at least, storm-related turbulence is the least dangerous kind because it shows up on radar and pilots can fly around it. The real problem is something else entirely. Clear air turbulence forms at cruise altitude, where jet streams cut across the sky at hundreds of kilometers per hour. Where 2 air masses of different temperatures and speeds collide, the boundary between them becomes unstable and chaotic. There are no clouds, no rain, nothing visible from the cockpit or the cabin window. The aircraft simply hits the chaos without warning. At 35,000 feet, a jet stream can shift direction and speed over just a few kilometers. That shift is enough to throw an aircraft violently. The FAA estimates turbulence injures around 17,000 passengers and crew in the United States every single year, making it the leading cause of non-fatal injuries in commercial aviation. The data has been there for decades. What has resisted every solution is the fundamental nature of atmospheric physics itself. Weather radar works by detecting water droplets, the rain and ice crystals inside storm clouds. Clear air turbulence contains none of these. To radar, a violent patch of chaotic air looks completely identical to smooth, calm air. There is nothing to detect because there is nothing physically there to find. The gap this creates is striking. A tropical storm system covering 500,000 square kilometers can be tracked 5 days before it makes landfall. A clear air turbulence zone covering just 50 kilometers at cruise altitude remains invisible until an aircraft flies directly through it. No satellite image will show it. No ground sensor will flag it. The problem runs deeper still. Clear air turbulence zones are not fixed structures. They form, shift, and dissolve within minutes. Even if a sensor caught one forming, the data would likely be outdated before the next aircraft arrived at that location. Predicting where clear air turbulence will appear is roughly equivalent to predicting exactly where a specific wave will break on a beach. Using only a photograph of the ocean taken 3 hours earlier, the system is simply too chaotic at the scale that matters. The first serious attempt at a solution came from NOAA and aviation weather agencies, which developed a system called Graphical Turbulence Guidance, GTG for short. The model analyzes upper atmosphere wind patterns and produces turbulence probability maps, updated every hour. For storm-related turbulence, it works reasonably well. Airlines use it to plan route changes around known risk zones before a flight even leaves the ground. But GTG runs into a hard wall when applied to clear air turbulence. The probability zones it produces are hundreds of kilometers wide. Telling a pilot there is a 40% chance of moderate turbulence somewhere inside a 300-kilometer corridor is not actionable information. It cannot tell them where inside that corridor the turbulence sits, how severe it will be, or exactly when it will occur. The resolution is simply too coarse for a useful operational decision. The deeper problem is measurable. Forecasting accuracy is tracked using something called a skill score, a statistical measure of how much better a model performs compared to a random guess. For storm-related turbulence, GTG skill scores are acceptable. For clear air turbulence, they drop sharply. The model that performs best against the turbulence aviation understands performs worst against the turbulence aviation fears most. If forecasting models cannot see clear air turbulence in advance, the next logical step is to use the aircraft themselves as sensors. Every plane that hits turbulence generates accelerometer data, precise measurements of how violently the aircraft moved. That data can be shared across the network in real time, warning following aircraft before they reach the same patch of sky. The FAA's pilot reporting system and Delta's partnership with the National Center for Atmospheric Research have both built networks that do exactly this, feeding turbulence reports back to routing systems within minutes of an encounter. On busy routes, this works. On a transatlantic corridor with dozens of aircraft following the same track, a turbulence report from the first plane can reach the second with enough time to adjust altitude or speed. The warning arrives fast enough to be useful. But on thin routes, where one flight might follow another by 3 hours or more, the data is worthless. The conditions that caused the turbulence have already shifted and dissolved long before the next aircraft arrives. And even on the busiest routes in the world, the system contains one flaw it cannot fix. Real-time reporting only works after an aircraft has already flown through the turbulence. Every solution tried so far protects the second aircraft. Nobody has found a reliable way to protect the first. The most promising technology currently being tested mounts a laser-based sensor called LiDAR, light detection and ranging, in the nose of an aircraft. Unlike radar, LiDAR does not need water droplets to work. It detects tiny variations in atmospheric density, and because clear air turbulence creates exactly those variations, it can potentially identify a dangerous zone before the aircraft enters it. Japan Airlines and Airbus have both been testing forward-looking LiDAR systems that provide between 60 and 90 seconds of advance warning before a turbulence encounter, enough time to instruct passengers to return to their seats and secure the cabin. Running alongside LiDAR is a second approach. Machine learning models trained on millions of historical turbulence encounters, combined with real-time satellite data, are beginning to produce clear air turbulence probability forecasts at resolutions that GTG cannot get close to. But several things must go right simultaneously. LiDAR systems need to shrink in size and cost enough to be fitted across entire fleets. Machine learning alerts need to be accurate enough that pilots actually trust them. A system that warns too often gets ignored. And the regulatory framework for automated turbulence response does not yet exist and must be built from scratch. There is also an important distinction worth making clearly. 60 to 90 seconds of warning is genuinely revolutionary compared to 0. But it is not prediction, it is earlier detection. The aircraft still has to be close enough to the turbulence for the laser to find it. That difference in terminology defines exactly what this technology can promise and what it still cannot. Every solution described so far faces a problem that is not standing still. Climate change is not simply a background condition for aviation. It is actively making clear air turbulence more frequent, more severe, and less predictable in terms of where it appears. The numbers are specific. A peer-reviewed study published in Nature in 2023 found that severe clear air turbulence over the North Atlantic has increased by 55% since 1979. The cause is the jet stream becoming less stable as the temperature gap between the Arctic and the tropics narrows, a direct consequence of Arctic warming. A less stable jet stream means more of the atmospheric chaos that produces clear air turbulence across a wider range of locations. This interacts badly with every approach currently in use. Forecasting models trained on historical turbulence patterns become less reliable as those patterns shift. Reporting networks built around known high-risk corridors face turbulence appearing in locations that were previously considered safe. Even LiDAR, which detects what is directly ahead rather than predicting what will form, cannot compensate for a simple increase in how often dangerous air appears. The industry is trying to solve a prediction problem that is getting harder faster than the solutions are getting better. And the clock is not neutral. Turbulence will never be perfectly predicted. That is not a failure of aviation technology. It is a statement about the nature of atmospheric physics at the scales that matter. The industry has always known this, and built a system designed to survive unpredictable turbulence rather than eliminate it. Aircraft are engineered to handle forces far beyond anything passengers feel in their seats. The question is not whether the plane survives, it is whether the passengers do. LiDAR deployment has been slow. Fleet-wide adoption requires manufacturer integration and regulatory approval that moves on aviation timelines, not technology ones. The 2024 Singapore Airlines incident happened after years of investment in turbulence mitigation technology. The gap between what is being developed and what is actually flying remains wide. The stakes of that gap are straightforward. Clear air turbulence frequency is up 55% since 1979. Passenger volumes are projected to double by 2040. If detection technology does not keep pace, the current injury rate, already thousands every year, will rise significantly. The maths is not complicated, so the question remains open. Will LiDAR and machine learning finally close the prediction gap? Or is the aviation industry quietly accepting that some turbulence will always be impossible to see coming? Tell us what you think in the comments. And if you want to understand how the aircraft itself is engineered to survive turbulence that nobody predicted, the wing flex limits, the load factors, the structural margins built into every commercial airframe, that story involves a test that Boeing ran on a 777 wing that most passengers would find genuinely difficult to watch.